Alright, in this video we're going to talk about the Nostartfiles flag, what it does, why do I need it in my bootloader project, that kind of stuff. Okay, I already did a take of this video where I fixed a problem that I did, fixed a mistake. Alright, the mistake was this. At the last video I was confused by how I deleted this flag and the build stage didn't work as I expected. So the problem was this. We've got a define flags here, which introduces the model of the CPU to my build stages. Here I got the linking stage and the compilation stage. I include these flags in the form of C flags in my compilation stage, but I do not include these flags. I did not include these flags in the linking stage, so that's why in the last video I was confused. So now it's all good. I also include this flag in the linking stage, and when we let's delete this flag to better understand what it does. So let's try to build the project and we get an error. What does the error say? It says on the linker complains, it says on this object file that I try to link, inside this object file, inside this section, at this point, there's an undefined reference to main, which makes sense. In my project, I don't include a main function. I don't have a main function, okay? My entry point instead is bootloader init, and this is intentional. There's a reason why I don't write main here. And the linker actually tries to link this object file, and it complains because this object file requires a symbol called main. So this object file is a special one, which is the default object file that includes stuff like interrupt vectors, stuff like initialization code, and a little bit of code that calls your main function. So if you were doing a normal project, normal Arduino application or a normal AVR application, you would actually use this object file. This object file would be useful for you. But in my case, since I'm writing a bootloader, I don't want the interrupt vectors, I don't want any extra initialization code, I don't want to call to a main function. I want my bootloader to run as soon as possible. So that's why I don't use the start files. And this is a good opportunity to actually investigate what this object file does, okay? So I got a command here. I got actually a script here that disassembles object files. So let's create a dump of the aforementioned object file and examine what it has, what it does, and examine this error, like what's in this init9 section. Okay. So all right, start file dump. Inside start file dump, we got a text section. After the text section, we got some like debug symbols, debug info, which do not interest us. Okay, we got a vector section. This one includes interrupt vectors. We got an init2 section, which includes initialization code, and an init9 section, which calls the main function that you are supposed to write. We can actually look at the code, look at the disassembly of them. Let's go here, vectors. Okay, inside the vectors, we got a lot of jump instructions. So generally, the way an interrupt works, so this is an interrupt vector, right? So general way of interrupts, general way how interrupts happen is when an interrupt request comes to the CPU, it jumps to a predefined address, which is called an interrupt vector. And typically, that interrupt vector address, suppose it's this one, typically it's just a jump instruction to the handler you are supposed to write for that interrupt, which is an interrupt handler routine, right? Like 4 bytes is not usually enough for an interrupt handler, so you just jump to your code that you are supposed to write for that interrupt to be handled. So this is why it's just a vector of jump addresses, and they are all 0. The reason they are all 0 is because they are unlinked yet. They are not linked yet. If we were to write a special named function for each of these interrupt vectors, at the linking stage, these jump 0 addresses would point to the functions that we wrote. Okay. And let's look at init2 section. Init2 section does some initialization to comply with C API. So GCC, when it compiles AVR code for C language, it actually requires the R1 register to be 0. It uses R1 register as a 0 register. Although the AVR datasheet does not constrict you to do that, but GCC usually likes a 0 register and uses R1 for that. So before executing or linking any C code, you need to initialize R1 register as 0 with the value 0, and then it initializes the stack register, stack pointer, so that you can make function calls reliably. But if you look at the data sheet, and let's search for stack pointer, the stack pointer is already initialized. So we don't need that code if we are fresh out of a reset. So actually I don't need this code in my bootloader project. I only need this. I still need this though. And here we come to the init9 section, and init9 section is where we got the undefined reference to main error, which is a call, there's a call here, and this call is supposed to get linked to your main symbol, wherever your main signal eventually gets linked to. Right now it says 0 because it's not linked yet. It's just an object file, not a fully linked file. Okay, so this is what this object file does. In a normal application, you obviously need this. You obviously don't want to overwrite the interrupt vectors. It's going to cause so many interesting problems for you. So you need all this code. Maybe your bootloader that runs before your application modifies the stack somewhat, so you need to reinitialize your stack so your application could work. All right, maybe we can talk about the default linker script and see those sections in action, right? So what does the linkers do with those sections when it builds the final executable? So what I did right here is we are no longer using my customized linker script. We're going to use the default one, and I'm enabling the verbose output so we can see the linker script. Okay, I'm going to build my project again, and hopefully this is going to output the linker script, the default one. And here's the linker script. Okay, let's examine this a little bit. Okay, original linker script. I already copied it right here. So we're going to search for the init2, the vectors, init2 and init9. So as you can see inside the text section, at the very top, at the very start, we get the vectors section. And the vectors is the interrupt vectors, as we saw in that start file, right? That object file. And we've got the init2, and there's a comment right here which says clear 0 register and set up stack pointer, which makes sense. We just talked about it, right? And in the init9 section, we get a comment here that says call main, which, right, this totally complies with the error we got. So this is what happens normally, but I use a customized linker script, right? I don't have init2 or init9 sections. I'll get a customized linker script. My linker script instead is a lot simpler. The text section starts from a customized location. What is this location? It's 7E00. We're gonna see why it's that. And the bootloader init section, which is a custom name that I came up with, it is at the very top. The first instruction of this section is the first instruction that runs because it's at the very top. Okay. Then we get the normal code that is in the text sections. So let's see why I chose this 7E00 value here. If you go to the data sheet, and we search for some configuration bit that's called boot reset, this controls where the CPU starts after a reset. So after a reset, I want my CPU to start at the bootloader section. And where is the bootloader section? We can configure that too through a configuration bit called boot size. If we input here 1, the bootloader flash section is going to be smaller. If it's 1, 0, it's going to be a little bit bigger and bigger. And what it is exactly is written here. So my configuration is the first row. The application flash section extends from 0 to this address, and bootloader flash section extends from here to here. And these are word addresses. They are not byte addresses, so we need to multiply this by 2. And let's do it. 3F200 multiplied by 2, we get 7E00. 7E00. Okay. So that's the start of the bootloader section. That's why I got this number. If I change this configuration though, if I changed it to 10, I would get more space for my bootloader program, but I would get less space for my application program. So that's why I use the smallest one, and with the smallest one, I get that address. Okay. Yeah. So that's why my text section in my project starts from that address instead of 0. For all of my binaries, I get a hex object dump. If you see the main elf, the first instruction of my main file is right here at 7E00. So it's the first instruction that gets run right here. And also, this instruction is special. We saw this at the special object file, right? This initializes the 0 register, which I still need to do it because I don't include the start files. So, in short, the Nostartfiles excludes system object files to be linked to your main project. So with this flag, you say, I don't want any system object files. I can take care of my own. So you say that. And when writing a bootloader, it's pretty useful. All right, thank you for watching.